Hello, my name is Adam Gray, and welcome to this lesson, Lesson 3.1, where we will get a chance to explore the applications of basic research and experimental design. Now, this lesson, given its 3.1, is probably one of the first chances you have had to appreciate Skill 3 as its own entity, its own skill, to be tested on the MCAT. And so, given that it's the first lesson, we're going to take things a little bit easy. We're going to define some key terms and see the scientific method at its basic level in action. But even though the difficulty of the content in this lesson may not be super high, it is really important that you know this like the back of your hand, because it's guaranteed that these principles and these definitions will underpin questions on all three of the science sections on test day. If you know them, it's going to be easy points. So let's get on the road to picking up those points, shall we? Our learning goals for this lesson, which we're going to cover in order with an exercise for each one, are first to recognize the scientific method itself and its various steps, and then to define two different binaries. First, to distinguish between testable and untestable hypotheses, and then to identify independent and dependent variables of each experiment. The science topics we'll see between the lines in this lesson are the biological basis of behavior and sensory processing. Now again, the focus of this lesson is not on these science topics themselves, but the examples that we see to illustrate Skill 3 will be in the context of this content. This is our first learning goal then, the scientific method itself. And we're going to learn it in the guise of a little story about two friends named Dave and Rose. You see, Dave is going to have a question, something he's interested in, and he's going to go about the scientific method in order to try to answer that question. Dave's story about this experiment is going to be spread over 3 paragraphs on this page or in this video across the next few screens, and you may already notice that there is some bold text here in these paragraphs. Each individual instance of bold text indicates an important step in the scientific method, as we will see. So here is your first chance to analyze Dave's thought process and his experiment. Read this first paragraph and then write down on your page what question Dave is trying to answer. Write it down in your own words. This paragraph itself shows the first 3 steps of the scientific method in the guise of this particular story. We see that Dave is fascinated by something. That means he has a question. His friend Rose has a really great sensitivity to hot plates. So what he does is he looks at the current research on it, but he still has some questions. And so he formulates a hypothesis. His hypothesis is that there is a certain amount of resistance built up when you experience something hot for a long time. Now, this paragraph doesn't exactly state what Dave's question was, but the basic question is, hey, why does Rose act so differently? And also, in the experiment he then designs, will the mice behave in this predictable way? And this is sometimes a neglected part of the scientific method as a whole. That is, you have to be interested by something, make sure the question that you have hasn't already been answered by someone before by doing research, and then formulating a specific hypothesis to test. So now let's see how Dave does test that hypothesis. Here is the second paragraph of Dave's story. The prompt is about the 2 different groups of mice. So read this paragraph and answer that prompt on your page. So in Dave's experiment, the mice have 2 groups. There's an experimental group and a control group. But the reason why Dave and all good scientists doing good experiments and yourself as you do your own research, probably in the past, but certainly presently and in the future, you need to have a control group so that you have something to compare against. And more specifically, it allows you to isolate the only variable that's being tested. In Dave's case, he kept 2 groups of mice that he kept completely constant as much as possible, except that he heated up the floor for one group of mice, the experimental group, but then didn't do anything special to the control group. This is the standard for basic science research. You take a control group, leave them as normal. You take an experiment group, and on them you perform the intervention that you are wondering if it creates a change. And that's what lets you test your hypothesis. Now, before we move to the third paragraph, I want to put some focus on, again, the bolded text here. It highlights 3 more distinct steps of the scientific method. First, the gathering of data, then the analysis of that data, and then finally using that analysis to make a conclusion. In Dave's case, he gathered data by splitting the mice up into groups. He analyzed the data by seeing the differences between the data in those groups, and he made the conclusion that, yes, the mice and his friend Rose are probably becoming acclimated or desensitized to that hot feeling after they experience it a lot. These are the last couple steps, but still important, of the scientific method. Read this final paragraph and fill in the prompt here of why these 2 steps are in fact important. And this prompt is a little bit less direct than the previous 2, so just do your best and then we'll see why they are so important. So we see here that the final steps in Dave's adventure are to publish his findings so that other people can see what he did and duplicate the experiment, and then to try to get the experiment verified by other people going through the same procedure. Now, in one sense, as the Kaplan tip says here at the bottom of your page, these aren't formal steps of the scientific method. You may have seen other lists of the method that don't include publishing and verification. But certainly for your career as a physician or a researcher, and also likely for some questions you may see on the MCAT, it's important to understand why these steps are important. And that's because research needs to be able to be reproduced. When other people run your experiment, they should be able to get the same results as you, because science is considerably less useful if it only applies for one result at one point in time ever. The purpose of scientific endeavor is to expand human knowledge and predict what's going to happen about the world. And that's why it's so important that results of one experiment can predict the actions of future experiments that are conducted the same way. Now, one more note before we move to the next learning goal about how this is actually tested on the MCAT. You are actually unlikely to see a question that directly asks you about one of the things in this story. This is not exactly an MCAT-style passage by any means, but it's still important to know the structure and order of the scientific method because it lets you predict what students might have done wrong in conducting an experiment. That happens a lot in MCAT passages, students kind of messing up experiments. It's also important because you are going to see a lot of experiments on test day. Most MCAT passages involve studies or experiments, sometimes multiple experiments in the same passage. That means you're probably going to see more than 20 brand new studies you've never seen before on test day. And you'll be able to handle those passages quickly and get the questions right if you have a mastery of the scientific method. To continue to build the mastery of scientific method that you need, we're now going to focus in on some details. First, on the building of a hypothesis. In the story of Dave and Rose, his hypothesis was that mice and his friend Rose would get used to hot temperatures and then not feel them quite as much. That was a testable hypothesis because he was able to say, if we expose someone, his friend Rose or a mouse, to hot temperature over and over again, then they will feel it less and feel less pain later on. Like most good testable hypotheses, that is an if-then statement. So in this exercise, we're going to go through 5 sample hypotheses, and what you're going to do is decide and circle whether these are testable or untestable. Let's start with the first one. It's about interneuron dopamine levels. This one, which we'll start off with as an example, is going to be testable. In fact, it's even phrased like an if-then statement. It starts with if someone experiences interneuron dopamine levels, then it's implied he or she will report an increase in positive affect. What you can do is you can take 2 people, you can see if they experience an increase, and then you can see, well, the people who experienced the increase, did they report an increase in positive affect? You can compare two groups, the people who experience the if and the people who don't, and then see if they experience the then. That's the very definition of a testable hypothesis. Let's move on to the next one. You take the lead this time, the one about Broca's area. Is this one testable or untestable? This one is also going to be testable. If you take this sentence and try to rephrase it, you can in fact rephrase it as an if-then statement. You could phrase it as, if people are speaking, then they experience more brain activity in the Broca's area. That is something you could measure by throwing people in a MRI machine and looking at their brain activity when they're speaking and they're not speaking. Very testable. And it's in fact true. Broca's area is a part of the brain that's involved in speech. Now, how about this third one? In particular, when you answer this, don't just circle testable or untestable, but know why you circled it. So, which one is this and why? This third prompt is in fact our first untestable hypothesis. In one sense, it can't really be rephrased as an if-then statement very easily, but more importantly, its results are not measurable. If the hypothesis is that the brain makes a spatial map on the occipital lobe, there's no way we can measure that. We can't go inside your brain and look at your occipital lobe exactly, at least not with current technology. And importantly, even if you could, the phrase processing visual images is very tough because the term processing is not very well defined. And even if you see certain activity in the brain, you can't be sure whether that activity contributed to the processing or whether it is simply occurring in confluence with whatever other stimulus you are presenting. All in all, it's a little too slippery and it's an untestable hypothesis. Let's take this fourth one, same as before. Is it testable or untestable? This one, like the first two, is in fact testable. You could rephrase it as an if-then statement. You could say, if people take this medicine, then they will feel better, and you could in fact design an experiment around it. You could have an experimental group who takes the medicine and a control group who takes a placebo. See if the people who take the medicine feel better the next day at higher proportions than the people who didn't. Textbook testable hypothesis. But now, look at the last one, which is similar to the previous one about nasal congestion and feeling better, but is different in important ways. This last prompt, is it testable or untestable? Now, just based on the fact that these are next to each other and so similar, you may have guessed this one is untestable, but it's important to know why. The difference between the fourth and fifth prompts are the fourth one is about people in general, but the fifth one is about me. If I take this medicine now, I will feel better in the morning. And the important difference is that the fourth prompt involves a large population of people, which means you can separate them into experiment and control groups and see large samples. But this last one, there's only one sample. There's just one person. It's just you. You can't split yourself into an experimental group and a control group. If you take the medicine, you may or may not feel better in the morning, but there's no way to know how you would feel if you hadn't taken the medicine because you don't have a time machine. And so even though it is a hypothesis, and it in fact is an if-then statement, you've got to be careful because it's not quite testable. You can't make a full sample out of it. You can't make experimental and control groups. And that's going to be key about testable and untestable hypotheses, both on test day and in the greater world of research. So the testability of a hypothesis is really important in evaluating whether or not something is worthy of research. If you have an MCAT question that says which of the following is the most appropriate hypothesis, or which of the following hypotheses is most testable or is untestable, these are all MCAT style questions you can see. It's not just about the testability, untestability as we saw in this exercise. There are other guidelines as well. And so now we're going to see 5 more criteria, one example for each, which help answer the question, is this a good hypothesis for a study? Based on just the headers of the 2 columns of this table, you can probably already see there's going to be something wrong with all 5 of these hypotheses. But the question here is not, is it a bad hypothesis, but why is it a bad hypothesis? As I mentioned before, this is going to illuminate 5 criteria, which collectively we call the Feiner method. And we'll see why it's called the Feiner method in just a moment. So let's start with this first hypothesis. It has to do with air quality. Somebody is hypothesizing, well, way back when air quality was better, people were smarter. Now, this is a hypothesis, but it's not a hypothesis that we're probably going to make a study about anytime soon. Why is that? What's wrong with the hypothesis? Well, the hypothesis isn't quite feasible. It's the same issue as an experiment with a sample size of 1. You don't have a time machine. We can't know if people born before 1800 would score higher on a modern intelligence test because none of them took modern intelligence tests because modern intelligence tests didn't exist when they were alive. It's just impossible. We can't design this experiment, even though it might be an interesting question. How about the second one? Placing neurons in carbonated soft drinks. Now again, somebody might want to know the answer to this question, but they're probably not going to get funding from their department to do it. Why not? What's wrong with this one? Now, there are a number of things that are wrong with this one of which is where are you going to get the neurons? But one problem is that it's not really of very much interest to the scientific community. Even if you got the results and you learned, hey, when you place neurons in Coke, they have better conduction than when you put them in Pepsi. How is that going to help design drugs or improve the human condition? Probably not at all. And so the resources you might spend conducting that study probably are better spent somewhere else. What about this third hypothesis? That when higher frequencies hit your ear, you perceive them as higher pitched sounds. What's wrong with this one? If you came to your department head with this study, why would they probably turn you down? Now, the answer here, though you may have phrased it a little bit differently, is that there's no new information to be learned here. We're pretty confident that higher frequencies are higher pitched sounds. In fact, you probably know that just from your own MCAT studies and basic science classes. Higher frequencies are higher sounds. So nowadays, you're not going to get the resources, and it's not really a good study to conduct for that reason. There are 2 more left. How about this fourth one? What's the problem with this study? This one might get turned down fastest of all because it's not ethical. When you're talking about a test about one person willingly harming another human, no, you're not going to get clearance for that. Interestingly, this study may remind you of some famous experiments you learned about in psychology class or in your readings for the MCAT even, but those experiments where people were harmed or very seriously stressed out are in fact famous largely because they helped define the ethics we follow today. Those types of studies, the Milgram experiment, the Zimbardo prison experiment, probably wouldn't get approved in today's day and age. That brings us to our last hypothesis with something wrong. This hypothesis is that pure gold, when you have 1 metric ton of pure gold, it becomes a magnet. Somebody wants the answer to this question, but why isn't it a great hypothesis to test? Now, based on the acronym at the top of the screen, you might have guessed what the first letter of this one is. It's because it's not relevant. Even if this hypothesis is true, nobody's ever going to use it for anything. Because if you had 1 metric ton of gold, you would probably do something different than use it as a magnet. And so the findings are not very relevant to the world around us. This reveals why we call it the Feiner method for judging whether studies are appropriate. Generally, a good hypothesis, in addition to being basically testable in that you can phrase it as an if-then statement, make control groups and experimental groups, should also be feasible, interesting, novel or new, ethical, and relevant. And those are the basic facts about hypothesis, design, and choice that will help you out for the MCAT. Again, you're unlikely to get an exact question that asks you about the Feiner method by name, but just having a deep in-your-bones comprehension of how and why studies are conducted the way they are will help you a little bit on a lot of the test. Because if you're helped a little bit on more than 20 passages across test day, that is absolutely going to translate to some points, to say nothing of how useful it is in your future careers. This brings us to our third learning goal for this lesson. And unlike the first two, the material in this third learning goal will almost certainly have questions about it on your MCAT. So we're going to define two terms: independent and dependent variables. You need to know the differences between both and be able to identify each in an experiment in order to get points on the test. What we're going to see here are three experiments, and we're going to identify the independent and dependent variables of each. We're going to use this first one as an example. You should probably recognize this experiment, this passage excerpt, because it is in fact the very experiment from our example with Dave and his friend Rose, where Dave takes a experimental group of mice and exposes them to hot cage floors, and a control group of mice who doesn't get hot cage floors, and then he measures their reactions, whether or not they've become acclimated to that stimulus. So we're going to use this as an example, because we're already pretty familiar with it, to identify the independent variable, which is what is manipulated by the experiment, and also what varies between the control and experimental group, and then the dependent variable, basically what is being measured or what we expect to change based on our hypothesis. So go ahead now and fill in the answers to both of these prompts on your page. What are the independent and dependent variables for Dave's study with the mice? Dave's independent variable is the floor temperature, whether he gives the mice a hot foot or not, and his dependent variable are the mice's reactions to that final test at the end of the week. One important detail here, that the dependent variable is specifically just the final test, because we get in this passage sample that at the final test was where he monitored their reactions. You might be speculating that the mice actually became acclimated over time, and so their reactions actually reduced over the full span, started off high, then gradually made low, but the dependent variable here is really just at the very end, because that's when he measures it. Here is our second experiment. This one isn't about mice, instead it's about rats, and it's about rats running through a maze, but go ahead and do this one. Read the paragraph and then fill in on your page what is the independent variable and what is the dependent variable in this study. This one might have been a little bit more challenging because we weren't given as much of the context of the experiment. Back with Dave, we knew his exact mindset, what his exact question was. But with this experiment, all we're given is this sample. Nevertheless, we can determine independent and dependent variables because they throw us a bit of a bone here. There are two variables explicitly mentioned in the sample: the experience variable and the learning variable. One of these is independent, the other one is dependent. The independent variable is the experience variable, or the number of times the rat goes through the maze, and the dependent variable is the learning variable, or how many mistakes it makes. So that means, in a way, we can reverse engineer the hypothesis or the purpose of this study in the mind of the experimenter, just knowing the variables. This experimenter probably has the hypothesis that as a rat goes through a maze more and more times, it's going to make a different number of mistakes. That is, if we see a change in the independent variable, we'll probably also see a change in the dependent variable. And to go even further, the result the experimenter probably expects is that the rats will get better. They'll make fewer mistakes. He's kind of showed his hand by calling it the learning variable, after all, that the rats will learn the maze and then make fewer mistakes. Finally, here's experiment 3. It's the hardest so far, but you can still do it. Read this paragraph and identify the independent variables. That is, in fact, plural. There's more than one thing the experiments vary, and then also the single dependent variable. This experiment is different from the other ones we've seen in the lesson because the previous ones had two groups that were being measured: experimental and control. This experiment has 4 groups being measured. Let's count them. First one is identical twins raised together. Second one is identical twins raised apart. The third one is fraternal twins raised together. And the fourth, this one was a little bit hidden, is the general population. We get in that last sentence that all those sets of twins were compared to the general population. And that's why this study has plural independent variables. The two independent variables here are genetics and environment. And having 4 different groups in the experiment allows us to isolate these 2 variables in any way we want, because identical twins, by definition, share genetics, and being raised together means the 2 siblings share their environment. The dependent variable then is what is in fact measured in each of these 4 groups, and that's athletic skill. Now, this final experiment is a really good example of how you can benefit from being experienced at what the MCAT is already likely to throw at you. As the Kaplan tip says at the bottom of your screen, there are certain studies and study design paradigms that are pretty commonly used in certain disciplines. When you're talking about the influence of genetics and environment, twin studies are absolutely par for the course. And while the MCAT doesn't expect you to know the results of every twin study in the last 50 years like the back of your hand, knowing the basic structure of twin studies, that they slice different groups in order to isolate the effects of genetics and environment by, for instance, comparing identical twins raised together and raised apart, not only helps you understand that content in the first place, the type of effects that genes have on our behavior, but also helps you take passages on the test in stride if they happen to be about the same subject. And those are the basics of research and experimental design as you will be tested on the MCAT. There's the scientific method itself, which has several steps: generating a good question, looking at previous research, making a formal hypothesis, collecting and analyzing your data and interpreting the results, then publishing and attempting to verify your results. Now, you don't have to list all of these by memory in order to succeed on the test, but you do need to be able to recognize each of these steps when you see them in a passage or a question, and that's exactly what our learning goal demands. We then saw the difference between good and bad, testable and untestable hypotheses using the Feiner method. Studies are more likely to be deserving of interest and deserving to be executed if they are feasible, interesting, novel, ethical, and relevant. Those were all those examples we saw about the metric ton of gold and the neurons embedded in different soft drinks. Sometimes, as much as it might be a personal interest, there is in fact a reason why some studies get funding and support and others don't. And finally, we saw the especially MCAT relevant topics of independent and dependent variables. The independent variable of a study is what is manipulated. In results, we generally see these on the x-axis. And if we have a good if-then hypothesis, the independent variable is generally the if part of it. And then the dependent variables are the other side of that coin. They are what the experimenter looks for and sees if we get a change. In graphical representations, they're generally the y-axis or the vertical axis, and in if-then statements, they are the then part of the statement. That dovetails to the biggest takeaway for this whole lesson, which is the purpose of an experiment. That is to answer the question, does the independent variable influence the dependent variable? If your hypothesis is that taking a certain type of medicine will help congested people feel better in the morning, then the main question is, does this medicine affect whether or not people feel better? The medicine is the independent variable, and feeling better is the dependent variable. And that's lesson 3.1. You'll get a chance to assess your progress on these learning goals in the assignments and homework connected to this lesson and in Skill 3 questions that you see in all your practice between now and test day. You can return whenever you need to, and once you've mastered this, you're ready to move on to more advanced Skill 3 questions. Keep up the hard work.